The use of polymers in the transport industry. Polymers are large repeating chains made up of a number of repeating monomers. For example, polyethylene is formed through the polymerization of ethene monomers. Copolymers are polymers made up of more than one monomer and can be statistical, which is random polymerization of the monomers, or block copolymers, in which the polymerization is controlled. Polymers are formed through two different processes, chain growth and step growth polymerization. Polymers are able to be used throughout the transport industry, and some examples include in planes, ships, cars, and the railway industry. Polyurethane. Polyurethane is formed from the condensation reaction between a hydroxyl group on a polyol and a cyanate group on an isocyanate, forming an ester and amide bond, resulting in a block copolymer. This polymerization is formed through the step growth polymerization, which can produce two different forms of polyurethane, flexible or rigid polyurethane. One form of polyurethane is rigid polyurethanes. Rigid polyurethane is formed between polyols of low molecular weights containing aromatic groups and aromatic isocyanates. Rigid polyurethanes are often found in thermal insulation in planes. Another form of polyurethane is flexible polyurethanes. Flexible polyurethane is formed between polyols of large molecular weights with alkyl groups and aliphatic isocyanates. Flexible polyurethanes are often found in car or plane seating, and the glycerol polyol is a common polyol to form these flexible polyurethanes. Rigid polyurethane is used in the thermal insulation of planes. Within this polymer, there is cross-linking and many hydroxyl groups. This is important as it leads to chain interactions and hydrogen bondings between the monomers, which decreases the mobility of the polymer. Within the polymer, there are carbonyl and aromatic functional groups alongside branching, which also leads to restricted conformational flexibility and mobility due to side chain rigidity. This means that to move freely, the polymer requires higher temperatures. Due to these properties of polyurethane, there is a high glass transition temperature. A glass transition temperature is when a polymer converts from the glassy state, a rigid solid, to the rubbery state, a flexible solid. Due to this high glass transition temperature, the temperature will almost always be below the Tg, resulting in a rigid and hard solid. It is in the glassy state. Because of the cross-linking and branching properties, polyurethane has a 90% closed cell, resulting in effective insulation as there are no heat or air passages, meaning that air is trapped. Furthermore, this will lead to less leakage of air and also protects the aircraft from dangerous temperatures. To form these rigid polyurethane foams, water reacts with the isocyanate that has not formed a polymer, forming carbamic acid. This then decomposes to form an amine and carbon dioxide, as seen in step 2 of the equation. The foam for thermal insulation is formed due to the production of the carbon dioxide gas. The amine then further reacts with the spare isocyanate, forming urea, in the second equation in step 3. Flexible polyurethane is used in the seats of planes and cars for comfort. Within this polymer, there is cross-linking and it is made from high molecular weight polyols and aliphatic isocyanates. This is important as it results in there being no chain interactions or side chain rigidity, meaning that there is conformational flexibility. Due to these properties of flexible polyurethanes, there is a low glass transition temperature. Due to the low glass transition temperature, the temperature will almost always be above the Tg, resulting in a soft and flexible solid. It is in the rubbery state. This is necessary for seats in planes and cars as the polymer will be soft, which is ideal for comfort and relaxation. The benefits of using polyurethanes in transport include how it is a lightweight polymer with a large mechanical strength, meaning that it's fuel efficient as there will be a high weight strength to weight ratio, resulting in less consumption of fuel than if a heavier polymer was used. The disadvantages of using polyurethanes in transport include how it's flammable and toxic, as harmful volatile compounds are released when under high temperatures arising from the isocyanates. Polyurethanes can also be viewed as unsustainable due to the fact that they are made from petrol resources. Polymers are also extensively used in railways. A few examples include PTFE in nylon in gliding plates, nylon 12 polypropylene in rail guides, and PTFE in pantographs. I will be focusing on the use of PTFE, also known as polytetrafluoroethylene, in gliding plates. The monomers that form PTFE are tetrafluoroethylene and are polymerized through chain growth free radical polymerization. This is where the initiator is broken down through homolytic fission by UV light to form two radicals. A radical then reacts with the tetrafluoroethylene to produce a polymer chain which can react. During the propagation step, the radicals add more monomers to the chain repeatedly to form polytetrafluoroethylene. PTFE can be used in railways as it is low friction. There are also weak dipole interactions, as are the large electronegativity of fluorine. This is because the electrons are unable to move and therefore form the dipole interactions, as they are held very closely to the fluorine. However, this does not affect the melting temperatures, as the chains are still held closely together, resulting in strong chain interactions. PTFE is also linear with no side chains. This is important as they are flexible single bonds, resulting in increased mobility and therefore a lower Tg. PTFE also does not fracture or age. The carbon-fluorine bonds are very strong, so are inert and hydrophobic. This is needed within a railway as the polymer is unreactive, weather and corrosion resistant, and is able to be exposed to high temperatures. The strong CF bonds mean that intermolecular forces do not form with other molecules, as seen through how the fluorine molecules are repelling the water molecules. However, there are strong chain interactions with each other, as seen here. Due to the fact that there are strong chain interactions, there is a very high melting temperature of 327 degrees Celsius. This means that it will not melt when friction occurs or when the tracks are exposed to high temperatures. The glass transition temperature is low, at minus 103 degrees Celsius, as there is mobility within the polymer due to there being no side chains and flexible single bonds. This means that the temperature will almost always be above the glass transition state, meaning that the polymer is in the rubbery state and will therefore be flexible and soft, which are not beneficial properties of the polymer for rail uses. As discussed previously, PTFE has low friction as there are strong carbon-fluorine bonds, meaning that intermolecular forces do not form with other molecules. The process of PTFE being low friction is observed through how PTFE and another material slide against each other, causing the PTFE to fracture. Pieces of PTFE are now shifted to the other material, and further sliding causes the PTFE pieces to become a thin layer on the other material. The original PTFE is also spread, forming a layer, meaning that both the material and the PTFE sliding against each other have molecules of PTFE which are arranged well. Therefore, the two materials can move against one another without friction. The low friction characteristic of PTFE is important as it can be used in gliding plates and railways. This allows the plates to slide smoothly. The resistance to heat and friction prevents an increase in temperatures on the train track. The resistance to corrosion weathering means that gliding plates will be wearable and not break down over time, resulting in a cost-effective method to be used in gliding plates. The benefits of using PTFE in gliding plates in the railway industry is that it's unreactive, meaning that it is resistant to corrosion and weathering. Disadvantages include how there is a low glass transition temperature, as under high pressures PTFE changes shape. It is also expensive compared to other polymers, and mass production of PTFE cannot occur. Now time for a quiz. Please pause the video to have a go at the questions before restarting to see the answers. What polymer is used in thermal insulation and how is it formed? Polyurethane, through the step growth polymerization of an aromatic isocyanate and a polyol. What type of polyols and isocyanates are rigid polyurethanes formed from, and how do they form foams? Polyols with a low molecular weight and aromatic isocyanates. Water reacts with an isocyanate, forming carbamic acid. This decomposition of the carbamic acid forms an amine and carbon dioxide. Why are polyurethanes good polymers for use in transport? They are fuel efficient as they are lightweight. What polymer is used in the gliding plates and railways, and how is it formed? PTFE, through chain growth free radical polymerization of tetrafluoroethylene monomers. How is PTFE low friction? PTFE and another material slide against each other, causing the PTFE to fracture. Pieces of PTFE are now shifted to the other material, and further sliding causes the PTFE pieces to become a thin layer on the other material. The PTFE is also spread, forming a layer, meaning that both the material and the PTFE sliding against each other have molecules of PTFE which are well arranged. Therefore, the two materials can move against one another without friction. Thank you for listening, and if you have any questions, please feel free to comment or take a look at the sources that I have used below.